All right, so in this video, we're going to be talking about thermochemistry. All right, there's a couple of issues about chemical reactions that we haven't talked about. So first of all, just because you can write a chemical reaction doesn't mean that it would actually happen. There's plenty of chemical reactions that I could write that would be balanced, but in reality, if you mix the reactants together, nothing would happen. All right. Secondly, even if a reaction does occur, it might not happen quickly. It might happen quickly or slowly. All right. For example, if you were to see like roadkill on the side of the road, we know that roadkill would eventually decay. All right, but it's a very slow process. So even though we know the reaction would occur, it would happen at a very slow rate. All right. Lastly, regardless of the speed of the reaction, sometimes it's possible that if you mix reactants together, only a portion of the reactants would react, and a portion of the reactants would remain unreacted. All right. So all of these things that I mentioned here are kind of some real-life considerations when you talk about chemistry. And what we're going to talk about first of all is what affects whether a reaction would actually occur. All right. So the answer to whether or not a reaction would occur has a lot to do with energy. All right, and that's why we've been talking about energy in this unit. All right. So a physical or a chemical change can be represented as what's called a thermochemical reaction. All right, and a thermochemical equation is just like the chemical equations that we've done before, except for in addition to the chemicals as reactants or products, we're going to express heat that's either gained or released in addition to those reactants and products. All right. So there's several ways to represent this, and just like when we're talking in the English language, we can have synonyms, which are multiple words that say the same thing. We can have multiple ways of saying the same thing with a reaction. So I'm going to start off with just drawing this. Wood plus oxygen gives carbon dioxide plus water. All right, that's just simply burning wood. All right, but one other thing that you should realize gets created is heat. All right, this reaction, if I were to cover up the heat part right here and just focus on this reaction right here, that's just the chemicals that get created. So does it make more sense to show heat as a product or a reactant? All right. Well, heat is created when you do that, so we would show it as a product. All right. Therefore, this is going to be an exothermic reaction. This is something that gives off heat. All right. In comparison to that, ice can turn into water. So where would heat go in that? All right, it's ice plus the heat will give the water. All right, that would be an endothermic process. All right, so recall that heat is a form of energy, and according to that law of conservation of energy, we can't just lose it or gain it. All right, so for example, I'm going to start off by saying that a piece of wood actually contains two forms of energy. All right. First, it contains thermal energy. All right. That's energy in the form of the kinetic energy or the motion of its particles. And that's what you would detect as its temperature. All right. Even though when we think of wood, we don't think of that form of energy, technically it's warm and could be used. You could use that heat to do things. All right. Most of the energy in the wood, though, is in what's called its chemical energy. All right, chemical energy is the energy that you could get out of that wood if you were to, say, to do a reaction with it. And the reaction that we often are going to think about is combustion. All right, so where is that energy in the wood? It's in the form of its chemical bonds. All right, so these forms of energy can be interconverted. All right, so could we turn chemical energy into thermal energy? Yep, that's what happens when you burn the wood. All right, so this is just a little review. Any process that releases heat is going to be exothermic. If it happens spontaneously, it would feel hot. Any process that absorbs heat is endothermic. All right, there should be a C there. If that process is spontaneous, it feels cold. I want to point out that for it to feel cold, it would have to be a spontaneous process. There are endothermic reactions that feel hot, all right, but they would not be spontaneous, all right. So since heat is a form of energy, it's going to be measured in joules, all right. As I mentioned before, there's several ways that you can represent a thermochemical reaction, all right, or a thermochemical equation. The first one was where we just mentioned heat, all right. The second one is going to show the heat by the exact amount of joules or kilojoules that it is. So, for example, if I show this front reaction right here, would this be exothermic or endothermic? All right. It shows heat being created as a product. All right, that means heat's being given off. That would therefore be an exothermic reaction. This one right here shows heat as a reactant. That would be an endothermic process. Okay, so the total amount of energy that any material has is what's called its enthalpy. All right, and enthalpy is represented by H. All right, you've noticed that we've talked about like the heat of fusion and the heat of vaporization. That's actually an enthalpy. All right, or it represents a energy that you're putting into or taking out of something. All right, so one way that you can think about the enthalpy of a material is just the sum of its thermal plus its chemical energy. All right. I just want to mention this is a little bit oversimplified, but for the purposes of this unit, this thinking of it that way will suffice. All right. So this leads to a third way of representing thermochemical equations. All right, is to show energy being released or created. All right. And that is to show the energy being released or created as a change in the enthalpy value, all right, or what would be considered a delta H. All right, so to give an example of how that would work, I want to give a hypothetical example. Let's say you take your wallet, all right, and in the beginning you have all the cash in the wallet, all right, and then you take $20 out of the wallet, and you have the $20 laying right next to the wallet. All right, so in the beginning, you've got the wallet. In the end, you've got the wallet with $20 laying beside it. All right, so the thing is that you should realize is that the total value of the wallet in the beginning would be equal to the total value of the wallet in the end plus the $20 that you took out of it. All right, so what we're going to do here, we're going to try to represent this by just saying, what is the change in the value of the wallet? All right, so let's pretend that we just took the $20 out. All right, we didn't write this thing down. All right, so cover up the $20. What happens to the value of just the wallet from here to here? All right, well, this wallet contains $20 less than this one right here. Its value has gone down by $20. So the change in its value in this process we could represent as minus 20. All right, that is the difference in the value from start to finish. All right, notice that when the change in the value of the wallet is negative, that's when money is being given off as a product in the process. All right, so let's compare that to this process right here. Wood plus oxygen is going to give carbon dioxide and water. This is the combustion of the wood, and it's going to give off this much in terms of heat energy. All right. Well, let's cover up this. Let's cover up this right here and just focus on the materials. All right. Which has more energy, the wood and the oxygen in the beginning, or the carbon dioxide and water in the end? All right, wood and the oxygen has more energy. All right, think about it. You can use wood to create heat because there's energy in it. You can't take carbon dioxide and water to create heat. All right, that it's basically like, think of these as like the ashes. It's what's left over after you get the heat out of the wood. All right, so let's just rewrite this and just have the chemical products. All right, we're not going to write the energy, the heat that's created in it. All right, so what happens to the energy value from here to here? All right, this has a higher amount of energy, this has a lower amount of energy. All right, the change in the enthalpy of the reactants to the products is negative. All right, so notice that when you have a negative delta H, that would indicate an exothermic reaction. All right, heat is being given off. All right, this can be a little bit confusing to people because when you see the H, a lot of times we think heat. All right, and when we see this negative number and we know it has something to do with heat, our mind thinks of negative temperatures. And negative temperatures we generally think of as being cold. All right, the thing about this is a process. A negative delta H would indicate that heat is being given off. All right, and that would feel warm. All right, so keep in mind negative delta H means it's an exothermic reaction. All right, and the reason that it's negative is that if you think about the materials, you are the heat value of the reactants going to the products. This has a higher amount of heat or heat energy here than you have here, so you're losing energy in going from beginning to end. That's why this is negative. All right. The last way to represent this is going to be what's called an energy diagram. All right, and so what we're going to do is we're going to represent enthalpy on the y-axis, and we're going to represent time on the x-axis. All right, so I've put some numbers in here that represent the amount of energy that these the reactants and the products have. And notice that in the beginning we've got the reactants, in the end we've got the enthalpy of the products. All right, so notice that the difference between the energy of the reactants and products is 520. All right, if you go from 720 to 200, that's 520. That's why that would correspond to this right here. All right, but notice that in this, it doesn't go straight from reactants to products. All right, you actually have to go up a little bit in energy before it comes back down and gives the products. All right, one way to think about this is to think about a match. Does a match just spontaneously catch on fire and give that heat off? All right, no. You actually have to put a little bit of energy into the match first to get the process started before the reaction will start going. All right, so that little increase in energy that you have to put into the reaction to get it started is what's called the activation energy. That would be represented by this right here, the distance from the reactants up to the top of this. All right, the difference in the energy of the reactants and the products would be the delta H. All right, and it would be negative for this diagram because the products have less energy than the reactants. All right, another way to think about what this would be is this would be the amount of heat given off by this reaction. All right, remember, if this has energy and the energy is no longer there in the products, the energy had to go somewhere. All right, and where the energy generally is going to go is heat that's given off by the reaction. All right, so I believe I mentioned that for this particular diagram, this would be exothermic because products are lower than reactants, and the heat that is lost between reactants and products is heat that's given off and is absorbed by the surroundings. All right, and we'll continue with the rest of this in another video.